Hello. In 12 seconds, Codeforces round starts. Okay, so let's go. What's happening? I don't get it. So we have a tree, we take a leaf, and we define its weight. String formed by the values of the vertices of the path starting at the root and ending at this leaf, and we calculate the difference between numbers of 1, 0 and 0, 1. Okay, this is basically same as we only have first and the last, so it's easy. The score of a tree is defined as the number of leaves with non-zero weight in the tree. It is just the number of leaves which are not the same color as the root. It's interesting. So it depends on if the root is colored or not, actually. So if the root is not colored, then both girls try to so let's basically draw it. So we have a root, we have several leaves, and we have some vertices which don't matter. Yeah, so we can color some leaf, we can color the root, or we can color a vertex which does not matter. Yeah, so we have, let's say, uncolored root, we have A, 0 leaves, we have B, 1 leaves, and we have C, question mark leaves. And what did we see here? Iris going first. Yeah, so and Iris wants to maximize, yes? Yeah, we want to maximize the number of different color leaves. So Iris definitely can make at least A plus B plus C over 2 floor. How? Well, she can just say that here we put minimum of A and B. So let's say that A is at most B. So she puts 1 here. And then she puts 0. And then she only uses 1 here. And this will be it. Okay, but sometimes she can do better. I think it's always just lower. I think it's always just what? Just maximum of A and B plus C over 2. I think that's the formula. Okay, let's try it. So T n So then we say that we find ans e. And the last string thing is string. Okay, and we need to print the answer. Yeah, so here we have IE. Yeah. So what do we do? So first of all, we need to find all leaves. So int root color equals -1 if s0 equals 0, then root color is 0. If it is 1, then it is 1. Yeah, then we go through degrees. Yeah, so we go through all edges and say that plus plus diag f.x and plus plus diag f.y. Okay, and then we take all vertices of degree 1. L leaves 0, leaves 1, and leaves question mark. So first of all, we check that it is a leaf. So if diag I is 1 is equal to 1, then if si equals 0, then plus plus l0, lzip s I equals 1, then plus plus L1, else plus plus LQ. Okay, first of all, let's say that in the root we have 0. So if root color is equal to 1, then we want to say that root color equals 0 and swap L0 and L1. Otherwise, our first player, what does she do? She puts in the root the minimum of 2 numbers, right? She wants to put in the root the minimum color. So we want L0 to be less than L1. So if L0 is less than L1, then swap is bigger than L1. Then swap L0 and L1. Okay, that's it. So now we need to put. Yeah, so we want to maximize L1 actually. We want to maximize L1. So the answer will be L1 plus LQ divided by 2, or usually. So if we move first, we can do one more. However, if root color is not set, then first we need to do it. And so we subtract 1, unfortunately. Okay, so sounds right. Let's see. 2, 1, 1, 1, 1, 0. Oh, 2, 1. Okay, here the answer is 2. And we printed 1. Why? we need to look at this tree. So we have 6 vertices. 1, 2, 2, 3, 3, 4. 5, 3, 3, 6. Okay, so we have 3 leaves, and let's color them. So colors are black if it's not decided, otherwise it's red and green. So question, so the only, so we have here, we have black. And we can guarantee 2. But how? We can color it. What can we do actually? So we have some other vertices, for instance, these 3. We can color these 3. Okay, if the total number of uncolored vertices, if the root is not colored, if here we have equal numbers, yes, so we have L0 equals L1. If we have root is uncolored, and we have LQ plus 1 plus internal uncolored, it is odd, then we can just ignore everything. We can just color these vertices. And if at some moment, so if our opponent does something here, so the moment someone does something here and here, they lose, right? They lose 1. So we can win 1 more in this case if internal uncolored vertices, their number is odd. Okay. So let's say int ans is this. Okay, but if root color is -1 and L0 is equal to L1 and internal vertices is, there is odd number of them, internal uncolored vertices is odd, then we say that plus ans. Good. So let's also calculate internal uncolored vertices. Okay, here we say else if si equals %, question mark, then plus in. Okay, now it should be 2 because the number of internal uncolored vertices is now 2. Yes. Okay, now it sounds great, but I don't want Rust. $112 people solved A. Well, okay, here I think it's problem. The problem is with what? We can't read. Okay, my my library is bad. Okay, this is not good. Ah, this also happens. Okay, we add 1 when LQ is odd. Only when LQ is odd. Yeah, for example, let's make the same tree, but I remove 6-3 edge. Yeah, in this case, we don't add 1. Okay, first of all, let's remove it and see that still I say that the answer is 2. I still say that answer is 2. However, actually, the answer should be 1. Yes. Sad, but okay. Okay, problem B, we have a rooted tree again with root at vertex 1. Yes, Iris did not know the values of Ti. Ah, there is an edge with weight equal to Ti. Again? What now? Okay, I claim that so I claim that we can get as many as this number. How? If root color is -1, then we color the root in the color equal to the maximum of to the minimum of 2 what? Sorry. So we have uncolored leaves. So first of all, we color the root, and then we color the leaves. Maybe sometimes we can do even better. No, I don't think so. It can't be. Actually, it can be written as LQ plus this is not equal to -1. Okay, we can't do that much, that many. Can we do even more? Sometimes we can. Sometimes we cannot color the root immediately. So, okay, first of all, the root should be uncolored. So this should be false. Yeah, and also the number of internal vertices uncolored, it definitely should be odd for us to do better. Well, I think it should be correct, the correct answer. Yeah, I don't understand what's happening. Oh. Maybe we need to look at some smaller trees. Let's look at some smaller tree. For example, two, starting with two. So we have definitely 1, 2, and we have, like, what can we have? We can have question, question. Okay, we can have everything. A 0, of course. Then a lot of ones. Okay, here it should be 0, of course. Why it is, did it, why was it 1? Okay, root color is 0. And we have L0 is 1. Ah, of course. A very stupid bug. Is 0, and here it should be... Yes. Very unfortunate. Yeah. Lost so much time. Okay, so in this round, already our result is based on how we do on harder problems. So we have several secret numbers on each edge. We only know that these secret numbers are non-negative integers, and we know their sum, which is W. Then there are n-1 events. We now know the weight of some edge. After each event, Iris wants to know the maximum possible value of the distance between two vertices, I and I mod n plus 1. It's basically W minus sum of all edges outside of this path, because we can just put zeros on all other edges. And she wants to know the sum of these n values. Nice. Okay, so let's see what we want. For two vertices, it's also DFS order. So let's look at our tree in some DFS order. It's like this and this and this and this and this and this, etc. So when we look at this edge, usually it will be an edge. We want we want maximum possible distance between these two vertices. Yeah, it's either just the sum of these edges if all these edges are covered. Or it's W minus sum of all these edges, which are not covered. If some of these edges is still unknown. Okay. So it's either one thing or the other. Okay. And what? Well, fine. It's not very hard to do. So basically, what do I want to say? I want to say that we have some paths, we have some chosen paths. On each path, there are some chosen edges, and there are the sum of weights of these chosen edges. Let's call it Ci and Ci. Also, we have Li, the length of this path, and we have the weight, which can be called Si. So we want sum of the following things. We have sum of the following things. So Si if Ci equals Li, or W minus Si if Ci is not equal to Li. No, not W minus Ci. W minus Si. But okay, we have also S, which is the sum of all already put edges. So then we want to say here W minus S and plus Si. So Si is always taken, but also sometimes it's W minus S. Okay. And we want to sum this and print these sums. Okay, how can we do that? For each edge, we just say on how many paths it lies. And actually, it always lies on 2 paths. So let's rewrite it. Let's rewrite it. It is sum of Si plus sum of W minus S, W minus S times sum of Ci is not equal to Li. Okay, these are 2 different things. So this is always 2 times S because of how DFS works. This is just always 2 times S. This is, however, a bit harder. So for each edge, we want to know on which paths it lies in this DFS order. And how many times? Yeah, we can write it like this. Okay. Okay, so let's read the graph and then we understand what to do next. So we read N and W. Then we read N minus 1 integers, the description of the edges of the tree. Okay, I can actually read here and subtract 1 from here. Yes. Then we read several pairs of events. And we need to subtract 1 from tx. Okay. 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 And in the end, we want to say that we have val ans is find ans of what? EEW. And we print it. Okay, so we need to return val given p, e, and w. Also it's PIL. Okay. So I want to calculate this strange thing. So I have, let's say that this sum is called U. So U is the number of edges, the number of pairs of vertices which are completely covered by our edges. Okay? So we say that it is U, which is initially 0. So then we have n minus 1 events. We do something. And then we basically say that ans I is what? Also we have LLS, which is also initially 0. And we say that it is 2 times s plus w minus s times u. And we return ans. So we want to change u and change s. So let's start with s. S is really easy. S is simply add EIY. And also we have u. So we always know that our edge lies on 2 Okay, I think I want to know the height of each vertex. That's what I want. Let's do it. So first of all, let's find the height of each vertex. So what is the height of I? It is 1 plus height of its parent. Its parent is stored in pi minus 1. Okay, we have found the heights. Then for each edge, I want to find on which pairs of vertices it lies. No, I want something like DFS actually. I want something like DFS. Yes, I want something like DFS. So for each edge, I want to know on which pairs of vertices it lies. To put it the other way, okay, it's kinda VVI on which it lies of size n-1. And let's go. So for int I from zero to n. So I consider the pair I plus 1% n. That's what I'm considering now. So if, let's say that int j is I plus 1% n. So if IHJ is greater than HI, then it's simply the edge between them. It's simply the edge between them. So I say that on which of j minus 1. Not j minus 1, but what? Yeah, j minus 1. So I have some vertex j, which is lower than I. This means that the edge between j and its parent lies on the path between I and I plus 1. How do we put it in this program? We say that on which of j minus 1 pushback of I. And also, let's say vi length of all n paths. So here I also want to say that li is 1. Let's also say continue. Okay. Otherwise, we need to step up several times and then probably step down. Okay, let's step up. Okay, let's step up. How do I step up? So while height of II is greater than maximum of height j minus 1 and 0, I want to jump from II to its parent. How do I do it? First of all, I say that on which of II pushback I say that plus plus Li, and then I say that II is parent of II minus 1. Okay, now II is either 0 as well as j. Let's also say int jj is j, and while jj is not equal to II, we say that on which of jj also pushback of I plus plus Li, and jj is parent of jj minus 1. So in the end, we have done this LCA process. We have done this LCA process. So now we know this and we know this here. Okay, what do we do here? For pair from on which of s of ei.x. So we consider all pairs of vertices. For them, we say that minus minus L pair. And if L pair after that is 0, then we say plus plus U. Good. It didn't work. Because on which is also incorrectly indexed. It's -1 indexed, as far as I understand. It's very bad, but let's deal with it. Okay, this is strange. This is very strange. So n is equal to 2, n is equal to 4. So now, for some reason, it is 11. Let's see what's happening. So we have an event of EI, which is E0, which is 1, 2. So we know that the parent of vertex number 1 is 2. Not the parent of vertex 1 is 2, but the edge to the top of 1 is 2. So we have vertex number 0, we have vertex number 1, number 2, and number 3, as far as I understand. And yeah, and we know that the sum of these numbers is 9. And now we know that it is 2. Okay, what is the maximum possible this value? This is basically 2. Then this is basically 9. This is basically 9. And this is basically 9. So it should be, of course, 29. 25. 2 plus 9 plus 9 plus 9. Yeah, it should be 29. What? I understand. This cannot be. This is 7. And this is also at most 7. Yes. So okay, 25 it is. So let's look at this formula. So S here is 2. So I claim it should be 2 times 2 plus 7 times the number of not covered. Not covered. Yes, not covered. Not covered. Okay, there are 3 not covered. 1, 2, 3. So it should be 21 plus 4 equals 25. Okay, not covered. So I think we start with u equals n minus 1. And here we subtract 1 if this is 0. Okay. Okay, now it's worse. Now it's 18 for some reason. Okay, n equals 4. We say s is 2. U is... U is n initially, yes. Okay, 25, 18, 18. 449, 302, 27, 2010. Yes. Yes, it's good. Hmm. Really? Oh, disgusting. What do we have in the standings? Or in here? 48 people solved it, so it's not that bad. Okay, so we have an array and we can add arithmetic mean of two numbers if there we have them. We want to check if we can have all numbers from minimum to maximum. Well, actually Actually, it's not very hard. I think, yeah, it's not very hard. So let's... I want to prove that it is equivalent to having two numbers, the difference of which What? It's just having at least three numbers, I think. It's strange, but really it's just having at least three different numbers. So assume that I have two numbers. Of different parity. So, okay, I have the minimum. I have the minimum. Let's... I have the minimum. The second number after that, for example, is... I don't have it. Let's just take the minimum, the second minimum, and the third minimum. That's what I want. Let's take the first minimum, the second minimum, and the third minimum. Yeah, I think I got it. I think that GCD of all numbers AI minus AJ should be a power of 2. That's my point. Okay, let's prove it in both directions. So assume that GCD of all possible differences is not a power of 2. Then it is divisible by some odd prime. Then I claim that actually you will never get... So if you get any number x, it is equivalent to AI modulo p. Just because if you have something modulo p and the same number modulo p, then their arithmetic mean is also the same thing modulo p. So if this is true, then you cannot get any... Then you can't get all numbers. Let's go the other direction. Let's assume that GCD of all these numbers is 2 to the power I. Then I claim that we can get all numbers. First of all, let's assume that so let's take the first minimum, the second minimum, and the third minimum. Okay, I want to change this triple. I want to change this triple somehow. Or it is I plus 1, I plus 2. So if if these two numbers are of different parities, then I can take the arithmetic mean. If these are different parities, of same parities, sorry, then I also can have the arithmetic mean. Otherwise, the first and the third number are same parity, and I can have their arithmetic mean. Then actually it is the same number as here. Fine. Then let's take the fourth number. And the same, with the same logic as before that, these have to be an arithmetic progression, and etc. So at some moment, I will stop having an arithmetic progression, and I can add a new number. Well, basically that's the end of the proof. So I want to find the number of subarrays in which the GCD of all differences is a power of 2. That's what I want. But how can I do that? Ah, it can be done with some segment tree. Yeah, it can be done with some segment tree maybe. Or I don't know. So we have a segment. How many segments with... So let's call it G of array is GCD of all its differences. So I want to find the number of subarrays here where this GCD is power of 2. So then I need to do it in the left part, in the right part, and also I need to consider the segments of this form. Okay, first of all, if this part is has GCD of power of 2, then we won. And if here, then we also won. Ah, it is something like 2 pointers, yeah? So I calculate all such GCDs and all such GCDs. And then I go from the biggest to the smallest. Ah, from smallest to the biggest. And try to move it up. So I increase this, then I move it as far as I can. Right? So what is the complexity? The complexity is f of n is 2 times f of n over 2 plus n log n. Okay? So this is, I think, n log square n. Yeah, I think it's n log square n, which is acceptable. So log is like 30, I think. No, not log square n, but log square n log n log maximum of numbers. So log of numbers is 20, log of, so 20 times 30 times 400,000. So it's 24 times 10 million, which is fine. Okay, maybe yes. So we have n, we read n. Okay, let's go. It's like find ans recursively from of a from 0 to n. Ah, it's not VL, it's now LL. Okay, so what do we do? Also, I want some auxiliary array. Which is simply to avoid reallocations. Okay, so we have LLANs. Also, we want some int m. First of all, if r minus l is 1 is equal to 1, then I have a segment of size 1, then it is brilliant. Yeah, if I have a segment of size 1, then it is immediately brilliant and I return 1. Okay, it's not of size 1. It's of size at least 2. I say const int m equals L plus R over 2. LLANS is find ans rec of A, B, L, M plus find ans. Okay, let's say it's ans L is this. Ans R is this. I have LLANS M is 0. And then in the end I'll say LLANS equals ans L plus ans R plus ans M. And return ans. Okay, I need to find ans M. So how do I do it? I have a segment from L to M minus 1 and from M to R minus 1. Okay, let's fill this part. So I say B M minus 1 is A M minus 1, and for int I equals M minus 2I at least L. BI is GCD of AI and BI plus 1. And then, similarly, I say BM is AM, and from I equals M plus 1, I is less than R, plus plus I. BI is GCD of AI and BI minus 1. Okay, I have done it. So now I have all GCDs that I needed. I have all GCDs. Not GCDs like this, sorry. Not GCDs like this. No, it is 0. This should be 0. No, it should not be 0. It should be it should be absolute value of AM minus AM minus 1. And BM minus 1 and BM as well. Yes, and here I say that BI is GCD of BI plus 1 and absolute value of AI minus AI plus 1. Here this and absolute value of AI minus AI minus 1. Okay, now it's fine. But it's not over. It's not over. It's not over. Okay, now what do I need? Now I need to consider all segments like this. And take here as small as I can. Yes? It's very hard. I don't understand, unfortunately. I don't understand nothing now. Okay, let's just write something. So I take all possible segments in the left part. The segment in the left part can begin at some point from m-1 to L. So we have segment from I to m-1. But we have left GCD equals simply BI. Then we want to ask in the right part, what is the smallest segment that we can take that still gives us okay. Initially, let's say that we take the whole right segment, right? So while CR is greater than, is at least okay. What do? We say that if GCD of left GCD and CR and BCR is not a power of 2, let's somehow write. So int current GCD is this. So if it is not a power of 2, that is CGCD contains something common with CGCD minus 1. Then we have to continue. It doesn't work. Otherwise, we say while CR is greater than M and GCD of left GCD and PCR minus 1 is still not a power. Okay, let's make a function. Power of 2 or power of 2 check. Return n and n minus 1 equals 0. So this is how we check that if we have a power of 2. So if it is not a power of 2, then we have to continue. So while this is true and this GCD is a power of 2, we subtract 1 from CR. And then we can add to the answer the number of segments that we can work with, which is R minus CR. Okay, I think we have finished this solution, although it took a lot of time. But we have finished it. Are you kidding me? Codeforces. Never. Always finds a way to disappoint me. Okay, 3, 18, 5, 1, 1853. So, okay, here we have 17 for some reason, not 18. But it should be easier to debug. Okay, so let's write 1. So for some reason it says 17, while the correct answer is 18. Let's calculate the number. So 1. Ah, I see. I see. So there are two types of segments in which this GCD is 0 and in which this GCD is not 0. So first of all, for some time it is 0, then it is. So I need to add two things. Okay, let's okay, let's say ans m non-zero, and then I need to add ans m0. These will be two similar algorithms, but still they have to be run twice. So if CGCD is not 0, then continue. Wait, what? Ah, I see. It's easier. It's really easy. So int 0 suffix equals 0, 0 prefix equals 1. Okay, for int I equals m plus 1, I less than r plus plus I. If ai equals ai minus 1, then plus plus 0 prefix, else break. And here start with m minus 1, and if I equals ai plus 1, then plus plus 0 suffix, else break. And then we say that ans m0 is 0 suffix plus 0 prefix times 0 prefix. Okay, now it's fine. Okay, problem D. Iris just has learned multiplication in her maths lessons, but her brain is unable to withstand two complex calculations. She couldn't multiply two integers with a product greater than k together. Okay. Good. Okay, so what does she do? Since here everything is at most k, then we just need to take several maxima and replace them with ones. And we want to find the minimum number of such maxima. Oh, data structures. Oh my god. Why do you love data structures so much, dear author? For instance, I don't like them as much as you do. So we have an array. We take some subsegment. And we want to find the minimum number of operations so that it can be rearranged as a1 times a2 is at most k, a2 times a3 is at most k, a3 times a4 is at most k, etc. Okay, for me, two types of rearrangements make sense. Minimum, so a0, an minus 1, a1, an minus 2, a3, an minus 3, etc. Or starting with an minus 1. So an minus 1, a0, an minus 2, a1. And it seems that this is better, simply because you can use a0 twice instead of once. Okay. or not. There is one more way, which is an minus 1, an minus 2, and then here a0 and a1. It's also nice. But okay, let's look at like this. Let's look at it like this. So here, what do we want? We want the following thing. So first of all, basically, always we have to take this and the next one because it is greater than the left one. So we want the following inequality. A I, where I means it's sorted array. Let's say that it is sorted array. So I want always AI times a n minus 1 minus I to be at most k. Yeah, so this pair should be at most k in the product, this should be at most k in the product, this should be at most k in the product, this one, and this one. What about the number in the middle? For example, a1, a3, a4, a2, a5, a2, a4, a3. So I would like to say that a3 should be coupled with a3. Yes, but it's fine because it is already coupled with a4 here. So this product should be at most k. So I claim that if it is false, then you cannot win. If this is false, then you just cannot win. Why is that? Why is that? That is because let's look at, for example, let's say that a3 times an minus 4 is greater than k. Then I claim that you cannot win. Why? Because let's look at 4 maxima. an minus 1, an minus 2, an minus 3, and an minus 4. So I claim that I can find no, what? So if n equals 7, then I don't want a3 and a3 to be coupled. What? Ah, because a3 is already coupled with a2. Ah, because I don't start with a0. I see. So a4, a0, a3, a1, a2. Okay, this should be true, except only if I is less than n minus 1 minus I. Okay, I assume, for example, like this. In general case, it's same. So if some two of these numbers are adjacent, then we have even the inequality that a something times a something is greater than k. Is greater than k, yeah. Where this number is at least n minus 4, and this number is also at least n minus 4. So even, and this is obvious because this is true. So these cannot be adjacent. Also, so let's draw a square around each element which is adjacent to at least one of these. So I claim that the number of squares is at least 4 here. Because if the number of squares is 3, it's the only way is that there is no squares here, and there is exactly one square between each pair. But this means that 3 is equal to n minus 4, and then it's also not interesting. So there are at least 4 squares, and this means that let's take the maximum square among them. It is at least a3. And it is touching some number which is at least n minus 4. So this is greater than k, and we lose. Okay, so basically it's equivalent. It's equivalent to what I said before. Okay, so we have some segment. We want that after the sort, all such products except the middle one times itself, they are at most k. This is what we want. Actually, it can be done with some square root decomposition. Yeah, for example, I have x1 ones. This means that a x2 is at least 2. ax1 is at least 2. And this means that ax1 times a n minus 1 minus x1 should be at most k. But here this is at least 2, so a n minus 1 minus x1 should be at most k over 2. Similarly, if I have xt times number 1 or 2 or 3 or etc. t, then it's true that a n minus 1 minus xt should be at most k over t plus 1. Let's put it another way. Let's also say that we have a y2. Okay, yi is the number of numbers such that I is at least, I is greater than k over I plus 1. Yt is number of i's that I is greater than k over t plus 1 floor. Okay, this can be easily calculated. Like 2000 times. Oh, we need a lot of memory, I think. Yeah, we need a lot of memory. How much memory we need? We need 10 to the 5th power times 2000. Yes. Which is 2 times 10 to the 8th power. This number of ints. This number of ints is 16 times 10 to the nth bytes. Which is this many megabytes. And we don't have so much memory. We can't store so much. So we need to somehow divide it 10 times. Yeah, we can do it, okay, at the cost of slowing everything down, but we can do it. Okay, so we now have some xi's and some yi's. So let's say that we have k, let's say that we have L equals square root of k floor. Yeah, so on each segment I want to know x1, x2, etc. x L, and also I want to know y1, y2, etc. yl, which is the number of numbers which cannot be paired up with this one. change. Number of numbers which are greater than k over L floor. Do we sometimes change the numbers? No, we never do it. Okay, so let's do it somehow and store all of this mess. What then? Then we're given some segments, so we know all these 2000 numbers. Now we want somehow to find the answer to the problem. What is finding the answer to the problem? So we several times take some number and make it 1. What does it change? It increments all x's and it decrements all y's. This is what it does. And after that, we want the following. We want y1 to be greater than x0, to be less than x0. I want y2 to be less than x1. To be at most x1, yes. y3 at most x2, y4 at most x3, etc. Okay, so there's still something strange in the end. For example, k equals 2. Let's see what happens if k equals 2. Then L equals 1, and x1 is okay. No, I don't like it. Let's say that we have, let's say that y I is the numbers which are greater than k over I t plus 1. So y1 can only be paired with this, y2 can only be paired with this, etc. Yl can only be paired with this. Okay, let's see what here we have. Now x1 is simply 1, and x2 and y1, the numbers which can only be paired with if we have an array 1, 2, 1, 2. y1 is 2. However, it's not true that y1 is at most x1. Yes? Maybe because there is an exception. So yi should be less than xi, but if their sum is equal to the length of the array, then it's fine to have an error by an addend of 1. Okay, this is awful. This is immediately a very bad problem. But I think I can implement it. So we have t and qk, and qk. Then we have b. Then we have L and R. So VPII D of size Q. PI minus PI dot x. And then we need to print. And that's it. So then we need to find the answer of vi ans equals find ans of b and p and k. And we print the answer. Okay, find answer vi given the array and the queries. So what do we do there? What do we do there? So first of all, we want to find number L. So we say int L equals, do I have sqrt? I don't? Why? Why I don't have int sqrt? Okay, let's say int sqrt key, then while y times y is less than k plus plus y, and while y times y is greater than k minus minus y. Turn y. Okay, I am interested only in numbers from 1 to L. So let's say that I do something. Hmm. Okay, I answer. So what we will do in our cycle? We will take some query. Then we want to consider only numbers from between these two between these two borders. Let's somehow call it auto evaluate prefix given int given the right border of the prefix, and it returns pair of vi and vi. Then if we can do it, what we do here, we say that we find pair vi vi for the left part. Eval pref of what? Of qr dot l x. Then right part. Then let's say that we subtract everything. So we say that left part, right part dot xi minus equals left part dot xi. And the same thing for y's. Okay, and then basically we do what I said in this this part of solution. So we say int current answer is 0. In the end, we will say that ans I is current ans, and we need to go through all these numbers. So what do we do here? We ask. So you have left part. Oh, right part. Now we only have right part. Actually, let's just call it xy, because it's shorter. Let's also say that const vi x is xy.x and const vi y is xy.y. So here we ask, we have xj and it should become at most yj. How many operations do we need for this to happen? We need to make several such numbers. So yj minus xj should be divided by 2. However, this only happens if xj plus yj is shorter than the length of the segment. So let's find the length of the segment, which is qr.y minus qr.x. So if this is less than len, then this formula. But if it is exactly len, then this formula. Good. Now we only need to write this function, eval pref. So for this prefix number p, we want to find an and for each like number from 1 to L, we want to find the number of numbers which are at most L and which are at least something. First of all, let's find the number of numbers which are exactly something is something. Okay? Ans. In the end, we will return ans. So here in the parentheses, we say this is vi L plus 1. And here we also say that this is vi L plus 1. Let me think. Yeah, we need some preparation. So let's make some arrays for the preparation. So we want for each 10th prefix just have the answer ready. As I said, this will be 10 to the 4th, yeah, because we divided by 10, times 2000 ints, which is simply 2 times 10 to the 7th power, and this is 80 million bytes, which is 80. No, this is 80 million bytes, which is 80 megabytes, which is less than memory limit, and it is fine. So let's say const int j equals 10. So we want to have our answer precalculated. Vector pair vi precalc of what size? Of size n equals let's say that n is b dot size, and here we say that it is n over j. So this is our precalc. Actually, I want n plus 1. And then I want pair vi of size vil plus 1 and again vil plus 1. Good. Now I want to fill it. How do I fill it? I go through I want to add a new number. So let's also say that I have pair vi current, which is also defined like this. So I have some number bi. I have some number bi. So where do I put it? So xi is the number of numbers which are at most. So I have bi. So in my car.xj, I want to store the number of numbers which are at most j. So if bi is at most j, then plus plus this car. Okay, what about the right part? So why do I say that y1 should be at most x1? And for example, y2 should be at most x2. So x2 is number of ones and twos. So here I want that the number of numbers. So this should be the number of numbers which are greater than k over 3. Okay? Number of numbers which are greater than k over 3. Okay, actually we have some problems here again. So for example, if k is 3, then we have 1. Oh, k is 4, for example. Okay, so we have 1 and 2, but actually 2 is greater than 4 over 3. So 2 it should be greater than k over 3, and it should also be greater than L, I think. I think we need to put it like this. Yes? I think yes. Okay, so let's write like this. So if bi is greater than L and bi, I think I need to store these numbers in a separate array. So let's call it borders. So a number is bad if it is greater than L and if it is greater than k over I plus 1. This is when my number is bad. Okay? So if bi is greater than capital BI, then it is bad and I add it here. Okay, and then if I%j is 0, then precalc I divided by j equals car. Okay? Okay. So now I need to evaluate some prefix. I need to evaluate some prefix. How do I evaluate some prefix? First of all, I need to divide it into two parts. Int left part, okay, medium. Medium is p minus how many numbers I can definitely calculate. P divided by j times j. So this number of numbers I can handle. Why? Because it is simply stored in precalc m divided by j. But before doing that, yeah, I will do that. I will do that. So I will go through 1 to L, and I will say that answer I, answer.xi plus equals precalc dot xi, precalc m over j. Okay, constant m is p divided by j, and here m times j, and here capital M, and same for y. But before that, I need to add all numbers. I need all numbers. I need all numbers here. So I need all numbers which are from M. Actually, here I need it to write like this and like this. All numbers greater than with index at least M. For int I is M, I is at most P is less than P. I need to add these numbers to uns. So how do I do that? Let's look at this number. If bi, there are two cases. Bi can be at most L. Then I add it to X. So where do I put it? I say that ans dot X bi plus equals 1. Else, I need to add it to Y. In the end, I will need to find prefix sums. Why do I need that? Just because I need. Okay, what do I do here? I want to find maximum t such that my number b is greater than k over t plus 1. So it should be at least this plus 1. Okay. Okay, this is fine. Let me think. So how can I rewrite it as an upper, an upper thing? So it is, I think, so a over b upper equals a plus b minus 1 over b lower. So I want to subtract the denominator minus 1. So k minus t over t plus 1 upper plus 1. B is at least this number. Then I can continue as b is at least k plus 1 over t plus 1. And this is equivalent of b equivalent at least just this. And this is equivalent. So I want max t such that this is true. So I want max t that t plus 1 is at least k plus 1 over b. So max t such that t is at least k plus 1 over b minus 1, which is simply maximum. What? Maximum t? Minimum t. I think I need minimum t. So this minimum t is simply k plus 1 over b like this, minus 1, which can be rewritten as k plus b over b minus 1. Oh, here, like this. Which is simply k over b lower. Good. So that's basically it. What? What? Ah, it should be j here. Okay, this is strange. From 1 to 10, it says that it says something that makes no sense. Okay, let's find some small segment where the answer is obviously off. Okay, 5 to 10. 5 to 10 is this segment. So this segment, the right answer is 1, but I have answer 2 for some reason. Why do I have answer 2? Let's try and see it. Or I don't know. So I want q equals 10. I want q equals 10. Okay, now I have it. So that immediately the first query is wrong. So here, so basically what does it say? It says that we need to make these three numbers ones. And of course it is true because now 7 and 1, 6 and 1, 5 and 1, 4 and 1, and then 3 and 2. But if 4 and 3, it would be bad. Left part is basically all zeros, and right part. Okay, xy, now what does it say? 0, 2, 4, 6. 0, 2, 4, 6? No. Why? How did it calculate such bad numbers? Ah, because precalc is 1 for some reason. Ah, because here it should be m and not m. Yes. Let's try again. Three, 3, 4, 3, 2, 2, 1, 1, 2, 1. Okay, I'm too lazy to check it further, so I will submit it. Okay, no, actually I can check it very easily. I can simply change this constant. For example, j equals 1. Let's see that if j equals 1, it's still fine. It's still fine. It's still fine. Then 2. E3. Okay, it's basically working. Also, let's try 100, just in case. 3, 3, 4, 3, 2, 2, 1, 1, 2, 1. Yes. Okay. Disgusting problem. Iris full binary tree. Iris likes binary trees. Let's define the depth as the maximum number of vertices on the simple paths from some vertex to the root. A full binary tree of depth d is a binary tree of depth d with exactly 2 to d minus 1 vertices. Yes. Iris calls a tree a D-binary tree. Some vertices and edges can be added to it to make it a full binary search of depth D. Note that any vertex can be chosen as the root of a full binary tree. Since performing operations on large trees is difficult, she defines the binary depth of a tree as the minimum D, satisfying that a tree is D-binary. Specifically, if there is no integer D at least one such that the tree is D-binary, the binary depth of the tree is -1. Iris now has a tree consisting of only vertex 1. She wants to add n-1 more vertices to form a larger tree. She will add the vertices one by one. When she adds vertex I, she'll give you an integer pi and add a new edge connecting vertices I and pi. Iris wants to ask you the binary depth of the tree formed by the first I vertices for each I from 1 to n. Okay, of course, we need at least one. Okay, first of all, no vertices of degree at least 4. So this is not acceptable if we have a vertex of degree at least 4. Firstly. Secondly, if only we have vertices of degree at most 3, then it sounds like it should be just we take all vertices of degree at most 2, take all of them, and try them as the roots. Then we take the maximum path from that vertex. Okay, no vertices of degree at least 4. Mon all vertices of degree at most 2. We try them as roots. We find the longest path from them to some vertex. And this is the answer. And for all vertices of degree 3, we do the same but add 1 at the end because, for example, if we have something like this. No, we don't do it. No, we only consider vertices of degree 2 or 1 and try them. And actually, whenever actually, yes. That's basically the algorithm. The problem is now it's quadratic or something like this because, or even cubic. So for now, I have a cubic solution. Consider my current tree, iterate over all vertices of degree at most 2, and check if they as a root have a small depth. Okay, let's say that I have some vertex as an answer. I have some vertex as an answer. So the answer is D now. So could the answer change? Could the answer have changed? So first of all, if some vertex of degree 3 became a vertex of degree 4, then yes, the answer is now -1. Assume that it didn't happen. So from this vertex, we know the distance to some other vertex, where there is a new leaf. So if this distance is exactly D, if it is less than D, then it is exactly, it is at most D, and this is fine, and the answer is still the same. The problem is if it was exactly D, and now I have an incremented answer. Well, it's bad. It is bad then. Well, I really don't know what to do. I really don't know. This person understands me. Guys, how do you solve this problem? Ah, I think I know what they mean. Okay, so let's call a length centroid the following thing. It is a vertex such that the depth of the tree is minimum in the center of this vertex. Okay? So I claim that there is at most 2 depth centroids. Yeah, because if there are at least 3 of them, then there are 2 of them. Then they look like this. So there are 3 centroids. Moreover, I want to say that if there are at least 2 centroids, then they should be adjacent always. Why? Because assume that it is not true. So there are 2 centroids and there is some vertex between them. Then I claim that it is a strictly better centroid than both of these. Why? Because so there is a longest path from this vertex and there is a longest path from this vertex. I claim that they should go through this path, because if they don't, so if there is a longest path from this vertex and it doesn't go here, for example, it goes somewhere here, then there is a longer path here, which goes like this. Similarly, the longest path here, if it doesn't go like this, then there is a longer path here. So both paths here go like this, start like this. And again, if it stops somewhere and goes somewhere. And it also stops somewhere and goes somewhere. Then instead of that, they could go like this and like this. So these two paths definitely overlap. They definitely overlap like this and like this. But then this vertex is better. Yeah, I claim that its depth is at most so its depth is at least one less than both of these. Yeah, because let's consider the farthest vertex from it. Yeah, so either it is farther from this vertex or it's farther from this vertex, of course, because if it's nearer to both of them, then it's strange. Okay, I think it's obvious. Okay, so there are at most two centroids, path centroids. So I have a tree. I have this path centroid, and I somehow store all distances from all vertices to this one. So if I add some new leaf, which did not change. So like for each child of this one, I know its depth. And let's say that all depths are at most d, and there is at least one which is exactly d, and there is at least one which is at least d minus 1. So this is d, this is at least d minus 1, and there are some else. So if I add something to smaller than d, then it is fine. If I add something to exactly d, but I have another d, then it is also fine. The only problem... actually... No, this is bad. This is actually very bad. This is bad because I really need a centroid of degree at most 2. Because if I have a centroid of degree 1, then it is hilarious and I don't need it. Or of degree 3. I still will need to recalculate answer after that, somehow. Well, I have an idea how it can be done. I have an idea how it can be done. Okay, so I have a vertex. I have its 3 children. At most 3 children. And it is a path centroid. So if there are at most 2 children, then the answer is obviously just the depth, which I know. Also for this vertex, okay, there are some strange data structures that I don't know. Haha. Haha. Well, but anyway, it's sad. I surrender. I surrender. Let's fast go through problems A to D. Problem A. Iris and the game on a tree. A tree rooted at vertex 1. Each vertex has a root of 0 or 1. We consider a leaf of the tree and define its weight. And it is defined as follows. So we write the string formed by the vertices in this order. we have a binary string, and we find the difference between such substrings 1, 0, there are 2 of them, and the number of substrings 0, 1, which is one of them, and the difference is 1. And for example, for leaf 6, it is 1, 0, 1, so the one such string and one such string, so the difference is 0. The score is the number of leaves with non-zero weight. So first of all, let's understand better what is the weight of a tree. So assume that you have a binary string. What is the weight of of the string? It's the difference between 0 ones and 1 O's. Notice that actually in any string there are 4 types of 2-digit substrings: 0, 0, 0, 1, 1, 0, and 1, 1. Also notice that in any string, it can be divided into several blocks. A block of zeros, then a block of ones, then again a block of zeros, again a block of ones, block of zeros, block of ones, etc. Okay, so inside of blocks we have such and such strings. Yeah, so 0, 0, 1, 1, they can only appear inside of blocks. 0, 1, and 1, 0, they appear at the bounds of the boxes, at the borders. So when we have that some block ended and some other began, we have 0, 1, if it is the finish of the 0 block and the beginning of 1 block. And when again 1 block is ended and 0 starts, then it is 1, 0. Notice it can be proved, for example, by induction, or you just can see it very easily, that basically the difference between the number of 0-1s and 1-0s is at most 1. Each time you have 0, 1, either you will get 1 back to 0, or the string ends with the block of 1s. So if the string ends with the block of 1s, then you have 0, 1, and then you don't have anything, like 1, 0 or 0, 1. But if this block of 1s is not the last one, is not the last block, then you have several zeros after that, so you have 1, 0 here. So what does it depend on? The number of zeros 1s minus the number of 1s zeros. What does it depend on? Actually, it only depends on the first character and the last character. So if the first character equals the last character, then the number of times that 0 was transitioning to 1 is the same as 1 transitioned back to 0. So 3 transitions from 0 to 1, but 3 transitions back. 3 transitions back from 1 to 0. If the first and the last character are different, then 0, 1 transitions will be one more than 1, 0 transitions. So this is the same difference, but of the string formed by the first character and the last character. And this is what I am claiming. You're only interested in the first and the last character. So the number of non-zero weights is simply the number of leaves in which the number is not equal to the number of in the root. For example, if in the root you have 0, then the weight of the tree is the number of 1s in the leaves. Okay? Therefore, actually, the colors of internal vertices, internal vertex is neither root nor a leaf. The colors of internal vertices, they don't matter at all. You're only interested in the colors of root and the internal and the leaves. Okay? So let's solve the problem. What is the problem now? It asks, in some vertices there are zeros, in some vertices there are ones, and in the rest of the vertices there are question marks. Dora and Iris play a game. On each turn, one of the girls, alternatively, replaces one question mark with 0 or 1. Iris goes first. And then Iris wants to maximize the score of the tree and Dora wants to minimize it. They play optimally, you need to find the final score of the tree. There are two cases, obviously. Two cases. First case is root is initially colored 0 or 1. So without loss of generality, let's assume that it is 0. So in the root, we have 0. Yeah, we still have some leaves. Zeros, some leaves ones, and some question marks. So let's say that we have L0 zeros in the leaves, L1 ones in the leaves, and LQ question marks in the leaves. So what is the strategy for Iris? Obviously, she wants to just take as many leaves as she wants and make them ones, so that these more leaves than in the beginning are different from the root. So Iris strategy, while LQ is greater than 0, take question mark leaf and color it to 1. This is what she wants, obviously. Also intuitively, it seems reasonable for Dora to color question mark leaves to 0. Let's prove that actually it's optimal strategy. To prove that it's optimal strategy, we'll find the answer in this strategy and prove that each girl can guarantee this answer. So the answer is actually L1 plus LQ over 2 ceiling. This is the answer. Let's prove that Iris can guarantee this number. So by Iris' strategy, she immediately she has already L1 leaves with not the same character as in the root. After that, she always takes some question mark leaf and colors it in 1. Note that if she does so, she will touch at least this many leaves. Yeah, because assume that she touched less than this number. For example, she touched K leaves, which is less than LQ over 2. So she took K moves, she touched, yes. Touched. I remember that during some of the previous streams, I say catched, while the correct is caught. So this was an error. But touched is definitely fine. So she touched K leaves. Dora touched at most K leaves, because she also had K turns after us. Okay, and after that, how many question marks we have? We had LQ question marks, minus K, and minus something which is at most K. This is definitely at least LQ minus 2K. And this is definitely positive because k is less than this number. So this is positive, and that means that Iris still has one more move to go. Similarly, Dora can guarantee that the answer is at most this number. To do that, let's notice that LQ is LQ over 2 plus LQ over 2 floor. So this is true. So to prove that Iris will touch and make one at most this number of leaves, we will prove that Dora can and will touch and make zeros at least this number of leaves. And this is done in similar fashion. This is done in very similar fashion. Assume that Dora touched less than this number of leaves. I will prove to you that she will have one more move. Yeah, because Dora made k moves, Iris made k plus 1 moves. So now LQ prime is at least LQ minus 2k minus 1. And again, if k is less than this number, then this is obviously positive. So after Dora's k moves and Iris's k plus 1 moves, Dora still has a leaf to color 0. So Dora will be able to color this number of leaves to 0. Then Iris will have at most this number of leaves to color them to 1s. Okay, this is the answer in the case when root is already colored, to color 0. The second case is much harder, and this is when the color of root is a question mark. Okay? Then I will give to you a strategy, and it almost always works. But sometimes it does not. Okay, Iris strategy. Iris strategy. Without loss of generality, let L0 be at least L1. L1 be at least L0. Yeah, because we can just swap ones and zeros, and the root is still uncolored. So without loss of generality, L1 is at least L0. So first move is color root to color 0. And starting with the second turn, while LQ is at least 1, color any leaf with question mark to 1. So this is our strategy. This is the strategy of Iris. With this strategy, she can achieve the following answer. First of all, she colored the root in 0. And after that, she's the second player in this game. And that means that she can color this many leaves in the color she wants. So the answer in this problem will become L1 plus LQ over 2 floor. Okay? Moreover, this is optimal when the first move is to recolor the root. So this is the optimal answer when the first move of Iris is to recolor the root. The problem is, sometimes it is not the optimal answer. Sometimes it is not the optimal thing to do. Sometimes it is not the optimal thing to do, unfortunately. So what can we do then? We will now understand when we can improve the answer and when we cannot. So first of all, I claim that if, so first claim, so this is, let's call it some answer. And optimum is some optimal answer. So sometimes answer is equal to opt and sometimes is not. First of all, I claim that if L0 is equal to L1, then answer is equal to opt. Why is that? Oh, sorry, well, L0 is not equal to L1. Yeah, when L1 is greater than L0. Why is that? Because actually, I can give to you some strategy for Dora. So the strategy for Dora strategy. Dora strategy is the following. So if Iris first move is root, then just color leaves in color 0. So if it is not, if it was not, then our first move is to color root in the color 1. And after that, color leaves in 1. Okay, let's understand how much do we get with this strategy. So in this case, if Iris's first move is color root in the color 0, and then we get, as it is written here, L1 plus LQ over 2. However, in this case, first case is Iris has colored root and exactly in color 0. So in this case, probably it is possible that root is already colored in 1. It's possible. So maybe it was already colored in 1 and maybe not. And then we have to spend a move on this. So what is our answer in this case? Yeah, in this case, yeah, we have. So ideally, Iris's answer is, if the root will be in color 1, the ideally Iris's answer is L0 plus LQ. However, we will subtract something. So how many accesses to the leaves do we have? We have this many accesses to the leaves. LQ minus 1, because the first move of Iris was probably touch a leaf, and then like this. Okay? So this is equal to L0 plus LQ plus 1 minus LQ over 2, which is equal to L0 plus 1 minus LQ over 2. Okay? Oh, plus, sorry, plus. So in this case, we can get this much. Okay, what does Iris do then? Iris makes the first move, so she chooses the maximum among these two numbers. So I claim that if L1 is at least L0, then she definitely wants to choose this one. She just always wants to choose this one because L1 is at least L0 plus 1 and LQ over 2 is equal to LQ over 2. So this is always better than this, or at the very least they're equal. So Iris really wants to choose firstly color the root into the least popular color among the leaves. Okay. If L0 and L1 are different, then this is true. When else we can say that it is true? I will tell you. The second case is that LQ is... let me think. So let's assume that L0 is equal to L1. The second case when they are still equal is that LQ is even. Then still answer is equal to opt. Okay? I'm still explaining problem A. This is ridiculous. Okay, when LQ is even, it's still true that answer is equal to opt. Why is that? Because I will now present to you a new strategy by Iris. Strategy by Dora. Strategy by Dora. Strategy by Dora. So if Iris colors a leaf, then we color a leaf in different color. Basically, that's it. If Iris colors anything, we color the root in any color. If Iris colors root, for example, in color 0, we color it in, we color leaves in colors 1 till the end. Okay? So this is the strategy by Dora. I claim that it always gets, if she does it, then we can get at most L1 plus LQ over 2 when LQ is even. Why is that? Simply because at the end of the day, the number of leaves different from the root will be at most, sorry, in color 0 we also color 0, of course. Let's understand that. So there are internal vertices, there are some zeros, there are same number of ones, as I said here. Yeah, I said here that if L0 is not equal to L1, then answer equals opt. Now, we also are assuming that L0 is equal to L1 and LQ is even. So there are equal numbers of zeros and ones, and also there are several question marks, and their number is even. We can even divide them in pairs if we want. And root is also uncolored. So as I said, so our strategy, if at some moment the root becomes... So there are two stages, okay, there are two stages of the game. In the first stage, root is uncolored. In the second stage, root is colored. So I claim that in the first stage, the number of L0 is always equal to the number of L1. Why is that? Because each time a leaf is touched, it is done by Iris. And she colors it 1. Then we respond with coloring 0. And if Iris is touch something inside of the tree, not the leaf, then we also do not touch the leaf. Therefore, in this stage of the game, L0 equals L1. And then when root is colored, the number of LQ is still even. Yeah? So the number of leaves is still even. And then we take the half of the turns and color half of these leaves in the color which is same as the root. The only case when it's not true is when Iris colored the root in the color 1, for example, and we then color some of the leaves in the color 1, because after that the number of question marks is odd. Yes, it is odd, but we are now we're now better than Iris, because now L1 is greater than L0, and Iris favors L0, so she's losing now. Still, she will be able to color the same number of leaves with 1 and 0, because she will color 0, we will color 1, 0, 1, 0, and now we want to color 1, but there are no leaves left. So basically in this case, LQ, because LQ is even if someone takes their time coloring the root in some color, it's still enough time for this person to make the same number of leaves 0 colored as their 1 colored leaves. Okay, so when LQ is even, answer is also equal to opt, because of this strategy by Dora. So now let's go on. Now we have three things. So now L0 is equal to L1, LQ is odd, and this is something that's often called Zugzwang in chess. Nobody wants to make the first turn. Yeah, for example, there are 3 leaves and there is 1 root. Nobody wants to color the root in color 1, because in this case, the other person, for example, which is Dora, she will color this leaf in first color. Then Iris colors this 0, Dora colors this 1, and now there is only 1 leaf colored as Iris wants, and 2 leaves which are colored as Dora wants. Okay, nobody wants to color the root. Nobody wants to color the leaf, because if someone colors the leaf, for example, in the first color, Iris colored in the first color. Then Dora colors this in the first color. Now Iris makes this 0, Dora makes it 1, and again Iris is lost because she only has one good leaf and Dora has two good leaves. Nobody wants to touch neither leaves, neither roots, so everyone wants to touch internal vertices. So in Zugzwang, you want to make a waiting move to pass the turn to your opponent. However, the waiting moves are usually not infinite. And in our case, it depends on Li, so the number of internal vertices. So I claim that if the number of internal vertices is even, then still answer equals opt. Why is that? Because, as I just explained to you, everyone wants to make waiting moves. Since Li is even, the number of internal uncolored vertices. So Iris will make a waiting move and Dora will make a waiting move. Again, Iris, Dora, Iris, Dora. And since this number is even, after we have ran out of the waiting moves, it's Iris's turn. So now Iris's turn, and now Li is 0. And she has nothing better than just color the root as it's said in this basic strategy. Yeah? Sorry, here. This is basic Iris strategy which gives this number, which we are calling ans. So when we have ran out of waiting moves, the best thing Iris can do is to color the root in any color she likes and get answer. So she gets ans. So that's why answer equals to opt. However, there is one last case. What is one last case? L0 equals L1, Li is odd, but this time, sorry, LQ is odd. But this time Li is also odd. And this means that actually Dora loses one more point. This time opt is ans plus 1. Again, they make waiting moves, but the last waiting move is done by us, by Iris. So Dora has to color either root or a leaf into a color. And if she colors a root, then it is the previous game. It is this game. And we get L1 plus LQ over 2 upper integer part. Or Iris colors some leaf, Dora colors some leaf, we color our root in the different color, and still it is the same answer. So basically it's almost always this answer, but sometimes it is ans plus 1 when these three conditions hold. And I have just explained why. Okay, problem B. Iris and a tree. Given a rooted tree with the rooted vertex 1, there is an edge connecting vertices I and pi, the weight equal to ti. The sum of all ti's is w, which is known, and all ti's are non-negative integers. One by one, the numbers on the edges become known, and after that we need to print what is the maximum possible weight, what is the maximum possible value of this sum of these dists. What is the maximum possible value of the sum of these dists independently? Okay. let's firstly understand something very basic. So you have several edges. On each edge, there is an unknown variable. x2, x3, x4, x5, some unknown numbers. You want to find, for example, distance between these two vertices. Distance between vertex I and vertex J. What can it be? So let's say that the known numbers here, their sum is sk. And the number of known numbers is ck. So let's consider two cases. First case is that ck equals edge dists between vi and vj. Edge dist is just the number of edges on the path between the vertices I and j. So the number of edges here is 3. So if all 3 edges are already known, then the maximum dist, the minimum dist, it is already known and fixed. It is just sk. So if no edges are unknown on this path, then the maximum distance is sk. There is a second case though, when there are several edges and there is at least one which is unknown. Yeah, for example, here we have one known edge and we know number x2, but we don't know still numbers x3 and x4. What is the maximum sum of this path? Basically, it's almost, we could always say that it is w, yeah? Because what it is still possible that just, for example, here we have x2 and here we have w minus x2. The only reason why it is not possible is because we have some other edges, mainly outside of the path. For example, if this edge is 1 outside of this path, then the weight of this path is at most w minus 1. It cannot be exactly w because there is already some unit outside of this path. Okay? Basically, all the weight except the known edges outside this path can be on this path. So I claim that maximum dist equals w minus the sum of all edges outside the IVJ path. How can we calculate it? Basically, so we have all edges, which is w. We have all edges, which is w. We need to subtract all edges which are already known and which are outside of this path. Let's for now subtract just all edges which are known. So S is the sum of known edges. And then we need to add back the edges which are on this path. As I already said, this is sk. Okay? So now we can say the following thing. We need to find the sum from... So as I said, as I didn't say, but I will say now, we are only considering the following n pairs. The distance between 1 and 2, the distance between 2 and 3, distance between 3 and 4, etc. Distance between n and 1. So let's iterate over all pairs from 1 to n. And we need to find maximum dist between vi and vi plus 1. So let me rewrite it. It is sum of either sk, si if ci equals edge dist between vi and vi plus 1, or it is W minus S plus Si if Ci is less than it. Now you can notice that there are both Ci's in the first and in the second case. So let's divide it into two parts. This part and this part. So here I will rewrite it as like this: W minus S times the indicator of the fact that Ci is less than edge dist of Vi and Vi plus 1. So we now need to treat these two things separately. We need to somehow maintain the sum of all SIs, and we need to somehow maintain this thing, because I can rewrite it like this: W minus S times the number of i's such that Ci is less than edge dist of Vi and Vi plus 1. Okay, so now we need to treat actually three things: sum of SIs, this number S, which also changes actually during the process, and this number. Okay, let's start with S. S is the easiest one. S is just the number of the sum of weights of known edges. Basically, it's just an integer which you store, and each time you get a new query, you say that S plus equals Y. S is increased by Y just because now you have one more known edge. So S is really easy. The second thing that I want to say is that actually this is also very easy. I want to say that this is always 2S. Generally, it's not true when you just take 1, 2 path, then 2, 3 path, then 3, 4 path, 4, 5 path. It's not true, because there can be edge which you traverse several times, like this. For example, there can be edge which is traversed 8 times, and some other edges will be traversed 2 times. However, in our problem, we know that this order is the DFS order, and if we take an Euler tour of a graph, sorry, let me reformulate. If we go among all vertices in this order, and this order is a DFS order, then it is always an Euler tour cycle on the graph. So each edge is exactly once gone one way and exactly one another way. Because when you run DFS, you always visit each edge twice, when you enter a subtree and then when you exit the subtree. So therefore, each edge is traversed exactly twice. So in each of these pairs, yeah, each edge is exactly in 2 of these pairs. For example, 3, 4 and like 7, 8. Again, because when you traverse an, let me write here, 2, 3, 4, 5, 6, 7. For example, this edge, we visit it twice. Once when we go from 3 to 4, like this, and once when we go from 4 to 5, like this. So this edge is gone twice through. Therefore, it is just 2s, and we can also maintain it because we can maintain s. So the last thing that we need to know is the number of such pairs I plus 1, between which all edges are already known, or not all edges are known. Initially, this quantity is n, because all ci's are zeros, and all edge distances are at least 1. Therefore, this number is exactly n. However, during the process, it changes. So what I want to do, so for each pair, let's make an array. Let's make an array. Let's call it L. L from 0 to n minus 1. So I want Li initially to be the number of edges, edge dist actually between vi and vi plus 1. However, during the process, it will not be just the number of edges between vi and vi plus 1. It will be the number of undecided edges, unknown edges. Initially, it's also Li. It's also edge dist. However, each time we take an edge on the path between vi and vi plus 1, this will be decremented. And if it becomes 0, then we need to add 1 to this variable. So we store a special variable called u. Initially it is n. And each time we see that some li was 1 and it becomes 0, it means that we need to subtract 1 from u. Because the number of paths on which everything is known is increased by 1, and the number of paths on which not everything is known is decreased by 1, decremented. Okay. The problem is, when we are given this xy query, which says that tx is y, this means that the edge between x and parent x, this edge is now known. We now need to somehow find both paths of type vi plus 1 on which this edge lies. So as I said, each edge lies on two paths. One path, for example, like this, and the other path like this. We need to find both of them. We need to find both of them. Okay, let's somehow find both of them. Between, as I said, it was between x and p of x. So, first of all, I claim that in any DFS order, in this tree, there cannot be x minus 1. There cannot be x minus 1. It is impossible. So basically, the first time when this edge will definitely be traversed is between x minus 1 and x. When you do it, you definitely visit this edge. The second time when you visit this edge is when you leave this whole subtree. So between maximum of subtree of x and this maximum plus 1. So if you iterate over all possible x's and find this is maybe not very pleasant. However, you can do it. So for each vertex, you can just find the maximum in its subtree, and then this and this are the pairs which are affected by this edge. The other way that I'm presenting is do it not x-wise, but pair-wise. So let's iterate over v1, v2, v2, v3, v3, v4, and each time for each pair we will find all pairs, all edges which lie on this path. And since the total length of all these paths is 2n minus 2, it is fast. So there is vi, and somewhere it is vi plus 1. So if height of vi plus 1 is 1 more than the height of vi, then it is just the sum of vi. And that means that there is exactly one edge on this path. The second case is the height of vi is not 1 more than 1 of vi. This means that we need to go up several times and then go down for vi. Vi plus 1. how many times? So if the height of this vertex is hi and the height of this vertex is hi plus 1, then we need to go up hi minus hi plus 1 times, and then we need to go down 1 time. And if you do it, it's very easy to keep track of which edges you visit. So when you go up from this vertex, you just always take x and px, and then here px and pxx, ppx, I meant. So you, with a cycle, store all these edges. And the same for this edge. The only difference, the only case when it's not true is when vi plus 1 is the root. Because in this case, you don't need to go down. You just need to stay in this vertex where you went. So vi plus 1 will be actually here and not here. But it's really easy to keep track of. You just check if your vi plus 1 is a root or not. So that's how you do it. For each edge, you store 2 paths which it lies on. And each time you have a query, you just take these 2 paths and subtract 1 from the corresponding allies. Okay, problem C. Array and expanded sets. Oh, okay, please. No, not please, I will explain it. What is the problem? So let's say that we have some array of numbers. Let's define the following procedure, which is called expand. We take all possible pairs of these elements. For example, I and j are 2 elements of this array. We take also the number I plus j over 2. If this is also an integer, we add it to this list, if it wasn't there before. Also, we consider our list as a set, so if some number is already there, and we add this number again, nothing changes. It was there and is still there. There are no 2 copies of it because we do not have a multiset, we have just a set. So while there are 2 numbers in our list such that they are in our list and their arithmetic mean is not in our list, we add it to our list. And we repeat it until it is possible. At some moment, we have added all numbers which we could. And this is the result of the expand operation. The list is called brilliant or something like this. Brilliant. Yeah, brilliant is called brilliant. Or adamant if expand of L is just a segment of consecutive integers. So like a plus 1, a plus 2, etc. b for some numbers a and b. In some order, of course, yeah, because set is an unordered thing. So if we sort it, it becomes just a segment of numbers from a to b. For example, 3, 6 is not a brilliant list because we cannot make any operations. And if we just take it as it is not all numbers from the minimum to the maximum. However, 3, 7 is a brilliant. Okay, 3, 7, 8, for example, it is a brilliant. Because we can make an operation between 3 and 7, which is 5, between 3 and 5, which is 4, between 5 and 7, which is 6. And now it is, we cannot make any more operations, but now it is a segment of subsequent integers. Moreover, 7, 3, 8 is also a brilliant array because it can be rearranged first 3, 7, 8, and then you can do everything as I said before. Okay, and now you have a segment. You have an array. You have queries of taking a subsegment and checking. No queries. Just you are given an array you need to find the number of its brilliant subsegments. That's what you need to do. Okay. I have explained the statement. Now I will explain the solution. The solution is as follows. Theorem. A list is brilliant if and only if one of two things holds. First thing, I'll say either set of L is 1. That is, there is only one unique number in this list. There are no two different numbers. All numbers in this list are equal. Or GCD over all pairs of numbers in this list, Li minus Lj, is a power of 2. For example, 2, 6, 8. Let's take the GCD of all possible differences. There are 9 differences in this array. 2 minus 2, 2 minus 6, 2 minus 8, 6 minus 2, 6 minus 6, 6 minus 8, and 8 minus 2, 8 minus 6, 8 minus 8. What are the differences? 0 minus 4 minus 6, 4, 0 minus 2, 6, 2, 0. If you take the GCD of all these numbers, it is 2. So therefore, the GCD of this array, the GCD, sixth GCD is 2. And it is indeed brilliant. For example, 4, 3, 5, 7. Now it is brilliant. Let me give you an example of a non-brilliant array. It is, for example, 4, 10, 13. So again, 9 differences. Let me only take 3 differences because there is no need to take the difference between the number and itself. And there is no need to take both a minus b and b minus a. So I will only take bigger minus smaller number. So 10 minus 4 is 6, 13 minus 10 is 3, and 13 minus 4 is 9. All these numbers, their GCD is 3. Therefore, it is not a power of 2, and this is not a brilliant array. You can add 7 here, but now you are stuck. You cannot make any more operations. Okay, the list is brilliant if and only if this GCD is a power of 2. Let me prove that. One way it's very easy. Let's prove that if it is brilliant. Okay, let me prove it the other way. Let me prove it that if GCD is not a power of 2, then it is not brilliant. Why is that? Because GCD is not equal to 2 to some power means that there is a sum prime p which divides this GCD. This means that all numbers a1, a2, etc. an in this array, they are all equivalent modulo p, where p is odd, and it is at least 3. Okay, all these numbers are equivalent modulo p. But this means that actually everything we can get from them is also the same residue modulo p, because x plus y is equivalent to 2a1 modulo p. And when we take the arithmetic mean, it is back a1 modulo p. Therefore, all your numbers in this array they are equivalent modulo p. So if there are only one of them, then of course this array is brilliant, but this is the first case. If there are at least two of them, for example, a and b, then a plus 1 is not in our set and will never be, because a plus 1 has different residue modulo p than a. That means that we will never have all consecutive integers that we needed, and this means that we have not a brilliant array. Let's go back. So if if GCD equals a power of 2, then it is brilliant. Okay, assume that the GCD is power of 2. Notice that when we make any operation, the GCD will still be a power of 2. Why is that? Because, so if we make an operation, we add some new number, z for example, and now GCD, before that it was GCD of some set of numbers and it was a power of 2. And now it is a GCD of some numbers and some new numbers, z minus a1, z minus a2, etc., z minus an. And it is obviously still a power of 2. Maybe it's a smaller power of 2, but it is still a power of 2 because even GCD of a is a power of 2. And if you add any new numbers, it will be a divisor of the previous GCD. And since the previous GCD is a power of 2, all these divisors are also powers of 2, so this is also a power of 2. Okay, so let's call a closure. Okay, let's just say that, let's say that our list is closed. That means that list is expand of list. This means that L is closed. So let's prove that if GCD is a power of 2 and L is closed, then L is a segment of consecutive integers. Why is that? What I mean? I mean, if we prove that, this means that initially, if L had a GCD of power of 2, then expand of L also has a power of 2. And by this theorem, this is a segment. And this means that this is a brilliant. And that concludes the proof that we want. So we want to prove the following fact. If we have a closed set, and GCD of all its differences is a power of 2, then it is a segment of consecutive integers. Or it's just a one integer. But it will also always be a sequence. First of all, if it's just one integer, then definitely this GCD is 0, which is bad. Because it should be a power of 2. Okay. Now let's assume that there are at least two different numbers. A, for example. Let me think. Okay, I want to prove to you that in any closed set is just an arithmetic progression. So let me prove it. Closed means that it is an arithmetic progression, also with odd difference. This is what I want to prove. Any closed set is an arithmetic progression with odd difference. Okay, let's take the minimum number and let's call it A1. If it is the only number, then definitely it is an arithmetic progression with or not difference. Let's take the second number, A2. Second by magnitude. Second biggest number, second smallest number, A2. So if A1 and A2 the same parity, then actually our set is not closed, because I can add their arithmetic mean, and it will lie between them. Therefore, it wasn't there before the operation. Therefore, my set is not closed. Therefore, A1 and A2, the difference between them is an odd number. Now I claim that it is an arithmetic progression with difference d. Let's go on. For example, okay, let me write something. So let's say that I is good. Let's say that we have an array A1, A2, etc., AN. Let's say that number I between 1 and n minus 1 is good if AI plus 1 minus AI is equal to D. So, as we know, 1 is good, because A2 minus A1, as written here, is equal to D. A1 minus A2 is equal to D. 1 is good. So there are two cases. All i's are good. This immediately means that we have an arithmetic progression, because all these differences are equal to an odd number. Second case is that not all AIs are good. For example, T is the minimum number which is not good. Let's take the minimum number which is not good. So A1, A2, etc., AT, they are all an arithmetic progression with a difference D. But then suddenly we have number AT plus 1, which is not which does not have difference D with these numbers. So here we have D, here we have D, here we have not D. Okay, again, let's consider cases. If AT and AT plus 1 have the same parity, then actually the set is not closed, because here I can put their arithmetic mean. This is the first case. The second case is that this difference is odd. But this difference is also odd. This means that this difference is even. Therefore, AT minus 1 plus AT plus 1 over 2 is an integer between this number and this number. Therefore, it should be somewhere here. It is not equal to AT, because if it is equal to AT, then actually this difference is also D, and we have an arithmetic progression. So T is also a good index, and we claim that T is the minimum not good index. Therefore, this is a new number which can be added, and therefore our set is not closed. So we have come to a contradiction. Therefore, indeed, when a set is closed, it is an arithmetic progression with an odd difference. Therefore, here we have an arithmetic progression with odd difference. But then GCD of all its differences is either 0. Let me write something. So let me remember you what we have. We have closed set A, and we have GCD of all I and j AI minus aj equals power of 2, it equals a power of 2. I claim that this means that it is an arithmetic progression. And this means I claim that this GCD is either equals to 0 if the length is 1, or it equals the difference of this arithmetic progression if n is greater than 1. Okay, this is impossible because, as I said, the GCD is a power of 2. Therefore, it is equal to d, where d is the difference of our arithmetic progression. However, we know that d is odd, as I have proven in the previous part. Therefore, this is an odd number. This means that this is 0 here. And actually, d is also equals to 1. It also equals 1. So I have an arithmetic progression with difference 1, which means that this is just a segment of consecutive integers, as I said. Good. So now we want to find the number of segments where this GCD is a power of 2. This is what I want to do. Or 0. So answer is the sum of two things. Number of LRs with GCD equals a power of 2 plus the number of LRs with all numbers mutually equal. So I need to find the number of segments with GCD equal a power of 2 and the number of segments with all equal numbers. Let's start with the second thing. It's very easy. We have an array. Let's cut it into blocks of consecutive equal integers. And then, if the lengths of the blocks are b1, b2, b3, etc., then this part of the answer equals sum of bi times bi plus 1 over 2. Yeah, simply because we need to find all ways to take a pair of indices in a segment. There are so many ways to do it. So the second addend is very easy. We now need the first addend. And it is done with a very basic divide and conquer. So we have, let's write an recursive function. Find recursive given a link to our array and LR and R between which we need to do it. Okay? We need to find the number of segments here with GCD equal to GCD of differences equal to the power of 2, some power of 2. Okay, how do we organize this recursive function? If R equals L plus 1, I mean, I always use half intervals, so like this, semi-intervals. So this is equal to L R minus 1 segment. So if R equals L minus 1, this means that I have only one number. And one number has GCD equal to 0, as we have already established. Therefore, return 0. Otherwise, let's take M somewhere. And let's divide our segment into two parts. This and this. So the numbers which are to the left of the mth number, where m is L plus R over 2. And the numbers which are m or to the right of m. So there are two types of numbers. Now the answer is the sum of three things. Segments that are completely here, segments that are completely here, and the segments which intersect this line. And they look like this. Okay? The segments which are completely here can be found by recursion. And segments which are here are also by recursion. Now we only need to find the segments here. This can be done quite easily. Let me explain you how. So we have our mth element. And here we have m minus first element. Let's, for all such element, find the GCD of differences of these arrays. And let's write them somehow. So the GCD of differences of this array, of this array, of this array, of this array, etc. For one element, it's always just 0. For two elements, it's just absolute value of this and this. So bm plus 1. Here it will be bm plus 2, bm plus 3, etc. How to find incrementally this GCD? So what do I mean by doing this incrementally? For example, let's fix some I and say that I know GCD among, not I, sorry, K. GCD of from I, from M to I, and, oh sorry, K. Assume that I know GCD among all I from M to K and J from M to K of AM minus AK, AI minus AJ. I know it. Now I want to know GCD among I from M to K plus 1 and among J from M to K plus 1, AI minus AJ. Okay? This is what I want to find. So I want to move this upper bound, K, one position to the right. This is the question now. Okay, how to do it? Well, we just increment. We just want to increment this K, this number K. Naively, you need to do it in linear time. Yes, so you need to add all segments of form AK plus 1 minus AI, or all pairs, sorry. You need to find GCD of all these numbers and GCD this number and this number. But this is too slow. I claim, so let's call it BK, and this is called BK plus 1. I claim that actually BK plus 1 is simply GCD of BK and, for example, AK plus 1 minus AK. Why is that? Well, we need to prove that the left hand side divides the right hand side and the right hand side divides the left hand side. The left hand side obviously divides the right hand side because here by definition we took all possible pairs of I and J. Here by definition we took all possible pairs of I and J between M and K plus 1. And here we only took these pairs and K plus 1 and K. We took only one possible pair with ak plus 1 instead of all possible pairs. This means that this is smaller, not only smaller, but bk plus 1 divides right hand side. Now I want to prove that right hand side also divides bk plus 1. Okay? How can I prove that? To do that, I can prove that right hand side just divides every such difference. So to do that, I need to prove that bk plus 1 divides any difference that can be met here. So it divides ai minus aj for all I and j in m k plus 1. Okay, there are two cases. So first of all, if I and j are from m to k, then obviously it is just a divisor of bk. Now, of course, right hand side if we only consider these pairs, okay, right hand side basically it divides bk. Yeah, just because bk is here. The second case is that, for example, I is k plus 1 and j is something. For example, j is j. Okay? Well, then I can say that bk plus 1 divides the following GCD. GCD of ak minus ak plus 1 and ak minus aj. It of course divides it, just because ak minus aj is met here and ak minus ak plus 1 is met here. Therefore, this bk plus 1 divides this GCD. And this GCD divides GCD of difference of these two numbers. Yeah? If you have GCD of a and b, it always divides a minus b. This is the main idea of Euclid algorithm. Therefore, it divides ak plus 1 minus aj. And this is exactly what is written here, yeah, because I is k plus 1 and j is j. Great. So actually, to calculate this thing incrementally, you only need to add to your GCD one more number, which is difference between this new element and, for example, previous element or mth element. Something like this. Good. So basically you find all GCDs like this and all GCDs like this. Now we just need to combine them somehow. Also, let's say that here it is not 0, but it is difference of am minus 1. Yeah, because definitely if the segment intersects this line, then it contains both m and m minus 1. And because of that, this number definitely will have to be in our GCD. Okay, now we have two arrays. So we have a cut point, and we have bm plus 1, bm plus 2, etc. Here we have bm minus 1, bm minus 2, bm minus 3, etc. We need to find the number of pairs of indices to the left of the line and to the right of the line, such that when you take this segment, for example, you take GCD of bm minus 3 and bm plus 1 here. This is a power of 2. You need to find the number of such pairs. Also, you know that to the right of this line, bm plus I plus 1 always divides bm plus I. And to the left of this line, bm minus I minus 1 always divides bm minus I. So these numbers go down to the left and to the right of this line. You need to find the number of such pairs. And this can be done with 2 pointers. It can be done with 2 pointers. So let me draw a histogram. So below each number, I will draw the corresponding b. So for bm minus 1, it is some column. Then they somehow go down, maybe the same sometimes. They go down, down, down. So the smaller and smaller number of divisors. And to the right of this line, this number is the same. And then they also somehow go down. Down, 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 down. You need to find the number of pairs of left column and the right column such that the GCD is a power of 2. The key idea is that if this is a power of 2, for example, then this is also a power of 2, this is also a power of 2, this is and this. So if this pair is good, then also all these pairs, these, and these, they are all also powers of 2. Therefore, my algorithm is as follows. I take, for example, some fixed column. I want to find here the leftmost column with which their GCD is a power of 2. And then I can add this number of columns to the answer. Then I take the next column. When I take this next column, the corresponding leftmost column here, with which this GCD is a power of 2, it moves somehow to the right. But you can do it with 2 pointers. You can actually look into my code where I show how it's done. Because when I explain it on paper, it's still not very understandable. So this is done here. So I have a function which checks that a number is a power of 2. Current right is the leftmost column, which has a power of 2 GCD with BI. Yeah, so I guess when I go to the left with my left column. So I iterate to the left through this column. So I take this one, then this one, then this one, then this one, then this one. Each time I want to find the leftmost column to the right, such that the GCD of left and right parts is a power of 2. I use here a variable CR. So if I was scrupulous, I would need to start each time with CR equals R minus 1. So each time I need to start with the rightmost column and go to the left, find something. Then again, start to the right and go find something to the left. Again and again and again. If I do it always starting with the right part, it would be in linear time, and in total it will be quadratic time, because each time I repeatedly go from right to left. However, since I know this condition, this condition and this condition, these two conditions, I know them. Therefore, I know that this function, the number of the leftmost good column, it is monotonic. Therefore, I can find all its values with 2 pointers, as I do it here. So I don't reset this CR variable back to R-1 each time. I do it only in the beginning, and then it can only go down. It can't go up anytime. So I can write this while cycle, and in the end I add to the answer the number of columns to the right of the leftmost columns. So this is my answer. Here I also have ans m0 because this part of the answer Sorry, where is it? Ah, okay, this part of the answer I also have in my recursive function. But it's kind of fine, although actually these are two different things. And in the perfect way, in the perfect world, you should do it separately. Okay, finally problem D. Finally problem D. Oh my god. Well, you really need to, if you want to understand this problem, you really need to look at the solving process, which was like 3 hours, no, not 3 hours ago, but like 2 hours ago, I think. You need to look at how I did it. How I was doing it. Basically, so the problem was as follows. You have an array. So first of all, let's have an array, AIs. A1, A2, etc., AN. So we want to somehow rearrange it. So now it looks like, let's say that it is already a rearranged array. And then we want the following thing. We want A1, A2 at most k, A2, A3 is also at most k, etc. AN minus 1 times AN is at most k. So all these conditions must hold. Then this array is good. Also, we call an array good if it can be rearranged in a way such that after the rearrangement, after some permutation, this holds. However, sometimes the arrays are not good. And then we say that like, let's see, cost of an array equals the minimum number of operations of form assign 1 to some number such that then the array is good. Let me remind you, when I say that it is good, it means that I can rearrange the elements in a way that now all these products are at most k. This is the cost of an array. For example, let me look at some example here. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and k equals 10. Okay, so the cost of this array is 3. Why it is 3? So firstly, I will change these 3 numbers to 1s. Then I claim that I can rearrange it so that the cost, I can rearrange it so that all these inequalities hold. I will do it the following way. 7, 1, 6, 1, 5, 1, 4, 1, 3, 2. This is how I do it. If I only change 2 elements, then the best thing I can hope for is is 8, 1, 7, 1, 6, 1, 5, 2, 4, 3. And unfortunately, there is this pair for 3, which product it's 12, which is a failure. Okay. Now let me explain what is the minimum, how to understand that an array is good. Sorry. Okay, actually, an array is good when the some certain and unique, actually, we don't need more than one. When some certain rearrangement works. So let's firstly sort our array. A1, A2, A3, AN. Let's sort it. And then we rearrange this array the following way. AN, A1, AN minus 1, A2, AN minus 2, A3. So this is, let's call it model rearrangement. So I claim that an array is good if and only if its model rearrangement works. How I will prove that? I will prove a system of statements, system of facts. So first of all, let's say that A is good if and only if there is some rearrangement which is good. This model rearrangement, let's call it M. Also, we can say that M of A is good. And if M of A is good, then definitely A is good because there is some rearrangement which works. However, I want to prove that these and these are equivalent. In order to do that, I will write something here, some inequalities, and say that inequalities are equivalent to MA being good. And if our RA is good, then these inequalities hold. If we do that, then as you can see, there is a cycle. From this follows this, from this follows this, from this follows this, and from this follows this. And we win. Okay, let me now write the system of inequalities. First of all, I will use zero. Okay, I will not use zero indexation because it will be fine as it is. Okay, I will now write here the system of several. So purple is obvious. Purple is obvious. Now I will write the system of several inequalities. And actually, I only need to prove it like this. Okay, the system of inequalities is as follows. A1 times AN minus 1. Sorry. AN times A1 is at most k. AN minus 1 times A2 is also at most k, etc. And we at some moment end. Where do we end? A n over 2 times a n over 2 plus 1 is at most k. So floor of n over 2 inequalities, this is what I need. Now we will prove two things. If these hold, then model rearrangement works, and if any rearrangement works, then this holds. Let's prove both things. Okay, let's start with this one. Assume that all these inequalities work. Then we need to prove that model rearrangement works. Basically, it's obvious. Let's go. This is at most k just because we have it in our list. This is at most k just because even if we multiply a1 by an, it is small. Then if we multiply a1 by something smaller, it is even more obvious that it is small. It is small as well. Then this pair, it is in our list. This pair is even smaller than this pair, therefore it is holding automatically. Let's go on. And at some moment we need to stop. We need to stop because we have gone to the right end of our list. And actually what happens there depends on the parity of n. So let's consider two cases. So n is even. Then what do we see at the end? At the end we see the following. We see a m plus 2, a m minus 1, a m plus 1, a m. This is what we see. So let me remind you what we know. We know that this inequality is just here. This is what is written here. This inequality is what is written the line above that. This inequality is obvious from this inequality. Or this inequality. From both of them, it is obvious that it is at most k. Great. So if n equals to m, then it is obvious. The harder case is when n equals to m plus 1. What do we have then in the end? So in the end, the last element will be the middle element of the array, which is a m plus 1. A m plus 1. Here we will have a m plus 2, a m plus 3, a m minus 1. Okay. So n over 2 here, which is... So the last inequality that we have in our list looks like this. A m plus 2 times a m is at most k. So this inequality, we know that it is at most k. This is also at most k. And we can see that it holds, this holds automatically and this holds automatically. Okay? So actually this complex of inequalities is what we need in order to say that MA is good. Now let's say that in any rearrangement, not only in the model, this is required. Let's prove that. Assume that there is some inequality which does not hold. For example, a n plus 1 minus I times ai is greater than k. Assume that it does not, so this happened in some rearrangement. There is some good rearrangement, but this holds. Okay. Let's take I biggest number, and also notice that I is at most n over 2 floor. Let's take I biggest numbers. Let's take I biggest numbers. Let's draw a square near them. Around them, I mean. So this is I biggest numbers. Notice that if any two of them are adjacent, then it is obvious, it is immediately a failure. Because they are at least a n plus 1 minus I times a again n plus 1 minus I. This is immediately at least a n plus 1 minus I times ai, because this is at least ai, and this is greater than k. So we have two adjacent elements with big product. Therefore, they are pairwise not adjacent. Okay, now let's take for each square, let's take the next number. Sometimes it is not possible. Okay, I just want to say that the number of their neighbors is at least I. So if we take all their neighbors without multiplicity, so if there are number, then some small number, and then a big number, then this is counted once. But still, I say that if we take all neighbors of these I squares, then the number of these neighbors is at least I. You can kinda consider cases. I will just say that the only way it can be less than I is that they are alternating. So there is a square, there are I squares. The first square is the first element, the last square is the last element, and between them they alternate with smaller numbers, and there are I minus 1 of them. Okay, the problem with that is that it's not possible, because it means that here I is actually n over 2 upper integer, and here we see, and since n is odd, this is n over 2 plus 1. And here we see that I should be less than this number, so we have a contradiction. So therefore, among these neighbors, there are at least I numbers. Let's take the maximum of them. For example, this number is the maximum. Since it is a maximum of some I numbers, definitely this purple number is at least ai. And this square is at least this number, because this is among I biggest numbers. So this product, as we know, is greater than k. So this product is also greater than k, and we again have a contradiction. So therefore, if there is at least one good rearrangement, then all these inequality hold. Therefore, array is good if and only if these inequalities hold. Okay. Unfortunately, in our problem, this set of inequalities is still not comfortable enough, convenient enough for using. So, because, yeah, now you can do it in like n square log n time. How? Q n log n time. For each query, you can take this subarray, you can sort it, and you can check all these inequalities. You can do it in n log n time for each query. So we have q n log n solution. O of q n log n solution. But this is very slow. We need to make it faster. I will now make it a bit faster. Instead of this, we will do something else. We will use the fact that k is small here. So let's understand these inequalities in some other way. So as I said, you can understand these inequalities in the following way. You just need to take this rearrangement, an, a1, an minus 1, a2, etc. Okay? So the basic idea is that if xy is at most k, this means that minimum of x and y is at most L, where L is square root of k floor. And L is small in our problem. It is at most 1000. Therefore, let's see what we can do. We can calculate the number of ones. So let's say that xi is the number of elements which are at most I. Okay? Now, okay, let's say that element is I bad if it can only be adjacent to numbers which are at most I. An element is I bad. Okay, first of all, sorry, let me say something. If a number is I bad, if it can only be adjacent to numbers at most I, and this number at least L plus 1. So numbers which are at most L, they are never bad. And number which is greater than L, it is called I bad if it can only be adjacent to numbers which are at most I. Why do I make such an inequality? Because let's understand two things. First of all, when is number I bad? I bad, the number is I bad if and only if it cannot be adjacent to, it is at least, first of all, it should be at least L plus 1, and it cannot be adjacent to I plus 1. This means that this number is at least, first of all, it is at least L, and secondly, it is at least k over I plus 1 floor plus 1. Let's understand that. So we take a number. It cannot be adjacent to I plus 1. Notice that if... So this number can be adjacent to I plus 1. But this number and any bigger number, if you multiply it by I plus 1, it is already greater. Yeah, because it is k over I plus 1 floor times I plus 1 plus I plus 1. Yeah, and this is k minus something which is at most I. So we subtracted something which is at most I, added I plus 1, and now it will be at least k plus 1, which is bad. So this holds. This holds. Number is I bad if and only if it is at least maximum of L plus 1 and k over I plus 1 plus 1. Good. Why am I saying that? this is an important definition. Because if you see this model rearrangement, let's see where I bad numbers can be. So for example, first several numbers are bad, I bad numbers. Then all these numbers should be at most I. Because if at least one of them is at least I plus 1, then this is a bad pair of a number which is at least I plus 1, and a bad I bad number. This is impossible. So after bad numbers, I bad numbers, there can only be numbers which are at most I. So I can rewrite it as follows. xi should be at least yi. Yeah, you see, because after every I bad number, there are 4 blue I bad numbers. There should be a corresponding purple or pink, I don't know how it's called, magenta number which is at most I. This means that xi is at least yi. There is only one exception to that. I will write it in parentheses. Or xi equals yi minus 1. And in total, this is the whole array. Yeah, because if this magenta and blue numbers is the whole array, then actually it's fine if here the array ends. You don't need one more magenta element after the end of the array. So if the array has ended, it's fine. Okay. Also, let me write one important thing. So first of all, array is bad if and only if for some I bad element contacts with number which is at least I plus 1. This is obvious. Array is bad. This means that in the model rearrangement there are two numbers which product is at least k. Yes? Is greater than k. This means that at least one of these numbers is greater than square root of k, which is L. So at least one of them is greater than L. And this number is I bad, where I is another number minus 1. Because it cannot be adjacent to I plus 1, basically. Okay. The second thing I want to say is that number cannot be L plus 1 bad. Why is that? Let me think. Can it? Number cannot be L. I mean, if number is L plus 1 bad. Sorry. Let me write something. So if number is L plus delta bad, then it is L bad. Let's understand that. So if number is L plus delta bad, then number x, then x times L plus delta is greater or equal than k. So if, well, where delta is at least 1. So this is greater than k. However, by definition, also we know that x is greater than L, and this is greater than L. So both these numbers are at least L plus 1 times, again, at least L plus 1. Right? So actually any number which is at least L plus 1, sorry, here plus 1 should be. Any number which is at least L plus 1, it is automatically L plus delta bad. And it is automatically L bad as well. I can write here 0. Again, any number which is at least L plus 1, it is automatically L plus delta bad for any delta. Therefore, we don't need any deltas greater than 0. We can just stop at moment L and say that number is L bad. So here we can actually say for some I at most L, I bad element contains contacts with I plus 1. Just because we don't need any badness greater than L, which is equivalent to badness, L badness. So to check if array is bad or good, we only need to check these L conditions, which are written here, basically. Because this is exactly what says that element, I bad element does not need to contact with I plus 1. Great. So, to check if subarray is good or bad, we need to find all numbers xi, all numbers yi, and check these conditions. Or this condition, or let me write here star. Star means exactly that here also can be xi equals yi minus 1 if their sum is n. Okay, what is the minimum number of operations that we need to fix the array if it is bad? Yeah, for example, xi is 2, yi is 6, and n is like 20. Or as they say, 20. They say, don't say t, 20. I'll say 20. What is the minimum number of operations that we can do to make this array good if this is the only, for example, bad pair? This is the only bad pair. Well, each time we take the maximum element and make it 1. Each time we do it, we subtract 1 from all y's. Yeah, because or either this y is 0 or maximum element is bad in this way, it lies in this y, and by making it 1, we subtract 1 from the number of bad elements. In the same moment, simultaneously, we increment I. Each time we do it, we increment I, because 1 can contact with everything it wants. Yeah, since all numbers are at most k, as you can see here. 1 can contact with anything, therefore we just 1 add to all x's possible. Okay? So we need to find the minimum number of operations to make x at least y. This is easy. This is simply maximum. Yeah, maximum of 0 and y minus x over 2 ceiling. There is only one exception. If x plus 1 equals n, then we need to change this formula, and now it's maximum of 0 and y minus x over 2 floor. Okay, this is the formula, and we need to take maximum among all i's. Okay. Now the question is, given an array and given its subarray, find fast all its xi's and yi's. Great. Well, it can be precalculated. Now I will write some solution which is not possible to get accepted with, but then I will fix it a bit and you will understand. So, for example, let's first find, I don't know, x5s. How to find all x5s? You need, for all segments, to fast find the number of elements there which are at most 5. To do that, you just precalculate. Let's say that p5 of I is the number of at most 5s from 0 to I minus 1. This array can be precalculated in the beginning. You can do it. So you spend on this precalc part O of O of n time and O of n space. How many such arrays you need? You need L arrays, which is O of square root of k. You need L arrays on x's and L arrays on y's. So in total, it's n square root of k. Okay? Great. This is precalc. Now we need to answer the queries. So each query, they ask you, what is the minimum number of operations to do with this subarray? So first of all, in O of L time, you subtract two P5s. For example, if it is from L to R, then you need P5R minus P5 of L. And this way you find the number of 5s, or at most 5s, on this segment. You need to do it L times, and you now know the array X and the array Y of a subsegment of our array. And then you just, for each pair xi, yi, find this and find maximum. So this is done in how much time? In time q square root of k. Okay? I think yes. So we can rewrite it as O of n plus q square root of k. How much time does it take? So n and q are at most 10 to the 5th power times square root of k, which is 10 to the 3rd power, and times some internal factor, which is like 4. And it is now 8 times 10 to the power 8. It is kind of fine because we have 3 seconds. Yes, so this solution works. Unfortunately, it does not work. Because when I said space, actually it was important. How much space does it take? So this step does not take a lot of space. Each time you need O of L space to make everything. However, this part, yeah, it's a huge precalc. You need all these n square root of k numbers, and it takes O of n square root of k memory, which is very much. Let's analyze how much it is in practice. So we need 2 times square root of k is 1000. This many numbers, this many arrays, times n. N is 10 to the 5th power. So this is 2 to 10 times 10 to the power 8 ints. This takes 8 times 10 to the power 8 bytes. And if you just divide it by million, you get 800 megabytes. 800 megabytes is more than we have. It's more than we have. So we can't afford this. I somehow got even 2 times more. I somehow got even 2 times more. How did I do it? I don't have any idea. So 800 megabytes is still too much. Let's improve our solution. So actually, I think there are billions of ways to make it take less memory. One of them is to make our precalc more sparse. So what do I mean by that? So we have an array of size n, yes? And for each element, for each subarray, you know something about this prefix. Let's not do that. Instead of that, let's know something about each tenth of our arrays. Each tenth. So we still take this much time to precalc it. However, we only store it in memory each 10th time. So it will, let's say that j is our parameter, which I say it is 10. So it takes O of n square root of k over j memory. Okay, how much time it takes? Still n square root of k time to precalc it. Let's look at each query. For each query, you still need to find a segment. And the segment is a difference of 2 prefixes, this prefix and this prefix. Let's look, for example, at the lower prefix. So this prefix is sum of 2 things, of this prefix and this segment. This prefix is precalced. So we can just take it from the memory. This segment is not precalced, so we need to spend time and recalculate. So for each element, we need to understand in which of these 2L numbers it makes some. Which of these 2L numbers it belongs to. There are 2 ways of doing it. For example, you can just for each of these j elements iterate over them, iterate over all these 2L elements and add. In this case, it will be q times square root of k times j time, which is not the best thing on earth because, for example, how much time we spent here? We spent here 10 to the 5th power times 1000 times 10, which is 10 to the 9th power. And at least it is times 2 because of the constant factor 2. And it is already too much. We don't want it that way. Okay, instead of that, you can make it j plus square root of k. And this will be fine. How to do that? Notice that if element is I bad, then it is automatically I plus delta bad for any delta at least 0. Similarly, if element is at most I, then it is at most I plus delta for all deltas. This means that actually internally, not internally, but semantically, our xi and yi are not arrays per se, but they are, they are prefix sums of some other array. So actually there is some here xi and here yi, EYI and EXI, such that xi is prefix sums of EXI, and this is prefix sums of EYI. So actually, we want to calculate this thing in O of j time, or j plus square root of k. We want to calculate this thing, and then we want to find prefix sums in square root of k time as well. So how to do it? There are two types of elements. So if element is, let's call it A. So if A is at most L, then it goes to some X. Moreover, it goes to XA. If A is greater than L, then it goes to some Y. It's actually very easy to calculate in which Y exactly. I deduced the formula during the contest. You can see it there. The answer was, well, let me see. K over BI. K over K over A. It is intuitively obvious because the maximum element that can be paired up with A is just K over A lower. Great. So for each element, it affects exactly one of these two arrays, and then you find xi and yi as prefix sums. Therefore, it will take this much time at memory. Moreover, basically you can even make j as big as square root of k. You don't change the asymptotics, but you now have O of n memory. So it's easy to make O of n memory solution and still at the same time asymptotics. So O of n memory and O of n square root of k plus q j plus square root of k. Oh, not j, now it's just n plus q square root of k. Okay, let me demonstrate it, for example. I put here j equals L. Let's try and submit it and see that it's still fine time, but now it's also much smaller memory. At least I hope so. However, yeah, see, it's same time, but now its memory is much less. It's much less. We didn't lose much because of this addend. Because since we have spent much less memory, it became fast because of that. Well, that's okay. The problems E and F I don't want to consider because I'm too tired and I really don't have any idea how to solve E. I will find it out myself. Other than that, have a great day. Thank you for watching.